Hello, I'm Alan Willison. I'm the chairman of the Hertford Astronomy Group, and it's my pleasure to welcome you to tonight's meeting. It's exciting times, isn't it, in astronomy, certainly in space exploration, with NASA having sent their latest probe off to try and deflect an asteroid. That's going to be interesting. And of course, on December 22nd, at the moment, we're looking forward to the launch of that famous telescope. It's going. So let's see if we can wish it well and look forward to seeing some startling stuff coming from that. Maybe they'll be broadcasting it as well, which I think would be good. You might remember last time we were here, I mentioned about photographing Uranus, and Richard very kindly sent me a picture of Uranus. There we are, a little blue blob. I mean, first of all, he did very well indeed to find a gap in the clouds, but to actually get out there and take a photo of it, I think brilliant. So thank you very much indeed, Richard, for sending that along and taking up the challenge. So this evening we've got a full programme as usual. In a few moments' time, I shall pass over to Martin Weston, who will give you a little talk about things that you can be looking forward to. And then we've got our guest speaker, Charlie Barclay, who will be introduced by Jerry, and he's got a fascinating talk as well. Following that, I'll have a few announcements for you about future meetings, and we wish, well, I'm sure you're all going to have a very enjoyable experience tonight. So without further ado, I'm going to pass over to Martin, who's going to take the next section. Over to you, Martin.
Thank you, Alan. Can everybody hear me okay?
Yes.
Just like to wish everybody a Merry Christmas and a Happy New Year. Hope you all enjoy yourselves and don't overindulge, obviously. Let's just see if I can get my presentation up. Yeah. So you'd think I'll be used to this by now, wouldn't you? Okay, so there we are. Can you all see Comet Leonard making a spectacular pairing with the bright globular cluster M3 there, hopefully. Cool. Brilliant picture. Fantastic. It's in the northern hemisphere sky. Watchers have a limited window though, so you know, if we get any clear evenings, it will be better through binoculars. Although it's probably it's fairly bright comet, but if you're in a light polluted area, it might not be so obvious. Yeah, magnitude 7. So I'm saying they're currently a binocular object around magnitude 7. But it will become a fifth magnitude as it travels eastwards between Boots and Serpens and Orphanus. So on here, hopefully on my next page, if it'll go, is the trajectory of it there. So you can see it then coming down through the inside of our orbit and close to Venus's orbit, and then heading back out again to the Oort cloud. So I put it to the Oort cloud, sorry. Comet Leonardo's orbit takes it out to the Oort cloud. Roughly, it's spherical repository of billions of comets that orbit the sun. I'm sure you all know that. Actually, the Oort cloud, which is an interesting factor that I didn't know, is actually a quarter of the way to Alpha Centauri. So it just shows you how massive it is. I mean, Alpha Centauri is over 4 light years away, so these are huge distances. 3,500 AUs, and AU is an astronomical unit. That's the distance from Earth's orbit to the sun. So on the bottom here, you can see if you're going to go out and look for it, where we are at the moment, we're on the 8th. So there's Arcturus, which is quite a bright star. It's one of the main stars for getting your position in the sky. It's past that now, and it's heading down Serpens, Caput, and down through there. So this is up to the 10th. Quite good viewing time. We just need a clear night. So that might be interesting if you get a chance to go out. So I recommend binoculars for that one. There's another comet. This picture taken by Damien Peach, who we've had several times come and give us talks at our society, and we're very pleased to show this wonderful image he's taken here. Not quite as bright as Leonard, but it's better placed in the sky. I didn't have time to work a path out for it, but what I can probably do is add something to the end of the talk about where you can find this. But so this is not as bright and it'd be more difficult to find, but quite spectacular. Right, this is an interesting one. I stumbled across the other day. They discovered a supermassive black hole with a huge mass ratio just outside our galaxy, in one of the dwarf galaxies that accompanies our galaxy. So the astronomers from University of Texas spotted a gigantic black hole at the heart of our galaxy's many dwarf satellite galaxies, meaning that in intergalactic times, it's just a stone's throw away from our solar system. It's been dubbed Leo 1, and it's roughly the same size as the suspected black hole we have at the center of our Milky Way. It's a bit of an oddball. By measuring the gravitational pull it has on the stars surrounding it, researchers found it absolutely massive compared to the size of its host galaxy. Well, that's just a little interesting factor. Quite like this picture I come across. This is someone taking a picture over Stonehenge. I'm sure you can all recognize that. And we can see Jupiter, Saturn, Venus, and the Moon all over Stonehenge. So I'm sure Dronescapes, who took this image, are very pleased with that. That would make a wonderful postcard or image, or even a picture on your wall. You'd be happy to have that on your wall, wouldn't you? That's really spectacular. That was just an interesting I came across. I thought you might like to see. So this was an interesting fact that I was going to bring to your attention last month, but unfortunately I couldn't make it. And it was just a discussion about Saturn's rings. I mean, Saturn's rings are iconic for us. That makes it highly recognizable for us when we observe Saturn in the sky. Even through a telescope, we can see the two appear to be lobes on the side of it, which make it instantly recognizable. But scientists have now discovered that the rings are slowly being dissipated. So I've just said there, if you were to pick Saturn out of the line, you'd probably recognize its iconic rings. They're the biggest, brightest rings in the solar system, extending over 280,000 kilometers from the planet, wide enough to fit 6 Earths in it in a row. But the interesting thing about this particular talk about rings is what's actually happening to them. Right now, it's raining over 10,000 kilograms of ring rain on Saturn per second, which is a phenomenal amount, fast enough to fill an Olympic swimming pool in half an hour. The rain is actually disintegrated remains of Saturn's rings, and probably most of you know, they're mainly made of ice and rock, and which are under constant bombardment from UV radiation from the sun and other tiny meteoroids. So there's a little bit of information about how long I think this is going to take for it to disappear. They're saying the drain will take 300 million years. Well, this seems like a long time to us, and it's not going to change much for our view of it. But in galactic terms, that's just a few minutes. It'd be interesting to see what Saturn looks like without its rings. This was a little bit of information I picked up about a mysterious comet. 29P was discovered in 1927, and it's actually orbiting the sun on a planet-like path as opposed to the comet path, which is normally in and out, sort of going around the sun and hitting perihelion and then diving back out to the Oort cloud. Its path space is between Jupiter and Saturn. It's also found to be very large, approximately 60 kilometers across. Later, astronomers found that it's behaving differently than other comets. Instead of shedding material as its outer layers melt during the flybys to the sun, it exhibits a kind of explosive behavior on occasions. Something was being ejected from the comet's interior, making the comet shine extremely brightly. The ejector then fell back to the comet, adding a coating. Further studies showed that periodically a much larger outburst would occur and the comet would shine even more brightly. So it's quite interesting to note that comets don't follow the same pattern every time. This one I put in as a matter of interest. We all tend to want to look at images of the sky, and we tend to think about them in normal visible light and what that reveals to us. We don't always realize that sometimes most of the detail is actually not available in visible light. So this image shows it quite well, I believe. So the top half of this image, which is showing a massive amount of detail, was all taken in infrared, which our eyes obviously can't focus on and we can't pick up. And the bottom half of it is in visible light. And that, so, I mean, I've imaged this Helix Nebula and it looks very much like this bottom part of the picture. But the top part of the image there is in infrared, and you can see how much detail is available. So it's quite important that all our space telescopes and ground-based observatories use all the wavelengths of light to assess data. We were talking about Uranus earlier on. Well, Neptune is the next and the last planet, according to recent updates in our solar system. But it was the first planet to be purely found using mathematics. I found this very interesting. Astronomers noticed a series of irregularities in the orbit of Uranus after its discovery and decided it could be caused by the gravity of a further unknown planet. John Couch and Adams of Britain and Urbain Leavitt of France separately predicted the position of the unknown planet beyond Uranus. Then a young astronomer, Johann Gottfried Galle, I think you pronounce that, and he studied Heinrich Louis de Arrest and decided to search for the planet based on the data received from Leavitt, and identified Neptune on the night of September 23rd, 24th in 1864. Interesting, the planet was approximately 1 degree from Leavitt's predicted position of 12 degrees from Adams' prediction. So it just shows you how maths plays a big part in studying orbital mechanics. A little bit about exoplanets here. This is one that just an artist's impression of a planet. And they found an exoplanet that is so close to its host star that its year, in other words, the time it takes to orbit the star, is only 16 hours. It's so close that it's second hottest exoplanet ever found after Kelt-9b, and the shortest orbit ever seen for a gas giant. The planet is doomed, though, already boiling hot and losing its atmosphere. Gravitational interaction with the star brings it ever closer. Eventually, it will be consumed by the star. Well, a very last piece of information I've got here for you. In a week, an asteroid will break into Earth's orbit, NASA. This month, an asteroid the size of the Eiffel Tower is hurtling towards Earth, and experts are calling it a very remarkable chunk of rock because of its closeness to Earth. The asteroid 4660 Nereus is designated as possibly the dangerous object. NASA anticipates it to be its closest point to Earth in 20 years on December the 11th. In 1982, the asteroid was found, so there's an image of the asteroid taken. And that concludes my presentation. I'll hand it back to you, Alan.
Okay, well, thank you very much indeed there, Martin. Some terrific information there and some great challenges for the astrophotographers in the group to get some of those asteroids into their vision, send them along to us. Okay, so with the James West Telescope set to do some infrared photography, I'm sure we're going to be looking forward to some more fantastic pictures like those ones we saw from Martin. I'm now going to pass you over to Jerry, who's going to introduce tonight's speaker. So, Jerry, over to you.
Thanks very much, Alan. And yes, I was thinking that there's the same thing, that we are really going to have so much to look for when James Webb finally gets into position. That isn't going to be for at least a month after its launch, because it's got a long way to go. And it will be probably another couple of months at least before it gets first light. But yeah, certainly something worth looking for. And I've got to say, that picture of Uranus was quite stunning. I mean, considering that for thousands of years, we didn't even know it was there, until it was spotted accidentally by someone in Britain, of course, we have to mention. But to get a picture like that, that's really something. So well done for that. So now I'm delighted to introduce Charlie Barclay, who is a new speaker to HAG, although he's been doing that to everyone else for a considerable time. He's a professional outreach astronomer, and he's been the director of the Blackett Observatory at Marlborough College for just very shy of 25 years. He's an academic visitor at Oxford Astrophysics, and he's an associate fellow at Green Templeton College at Oxford. He's a fellow of the Royal Astronomical Society, and from 2017 to 2019, he was the president of the society. He is also chair of examiners for GCSE astronomy and the UK team leader for the International Olympiad on Astronomy and Astrophysics. Surely we should all be taking part in that. Perhaps you might mention something about that, Charlie. But tonight's main topic is Henrietta Leavitt, who died, we're just a few days short of the 100th anniversary. And we're going to learn how the work that she did was incredibly important in, just as Uranus practically doubled the size of the solar system when it was discovered, her work has greatly increased our knowledge of the true size of the universe. So over to you, Charlie.
Thank you. I've unmuted. If someone could just make sure that I am being heard, so hopefully that's okay. Thank you. Well, thank you, Jerry, very much for the introduction. I should just add that I was vice president of the RAS rather than the president, although it's nice to have that extra accolade, but vice president was quite busy enough. Thank you. So I'm very sorry that I'm not with you all face to face to give you the talk. I mean, we're all living in strange times. I'd have liked to have seen where you operate and where you are. I know about you as a group. It's been a name that I've heard. So, and Jerry, we've met in the past, I know. Of course, talking over Zoom has many advantages. You guys can all be snug at home. You could have a nice cup of something hot. You can mute yourselves, which is good. You can mute me, which might be even better. So these are great advantages of Zoom talks. For me, it's not such an advantage because sitting here talking to a computer screen is odd, and I hope no one's going to come through the door because it looks very strange. But there we go. Look, this is a different sort of talk to the one I usually do. It's not primarily sort of observational astronomy or astrophysics or anything complicated with equations, and that'll probably help a few. But it's more historical in its content. Now, please don't blame me for variations in dates, because as an astronomer, I'm pretty happy with error bars of plus or minus a million years or so. So when I'm talking about a few tens, that could be not so good, but I'll give it a go. So this talk was invited and indeed prompted, as Jerry said, by the 100th anniversary on the 12th of the death of Henrietta Leavitt, who I think, in my view, is the most important forgotten astronomer. And I'm going to try and cover some of her work and the background to it. And indeed, I'm also going to choose four, of which she's one, key women who have are forgotten heroes of astronomy. My choice is entirely personal. I'm sure others might choose differently. I'm going to focus on 20th century discoveries, though I will refer to earlier stars. I'm going to talk for about 45 minutes and then very happy to answer questions via the chat facility at the end. So tonight's talk is also motivated. Oh, I'll tell you what I need to do is, of course, share my screen. There you go, and you'll get the slides. So hopefully the share screen will work, and then we can go to the start there. Now, I hope that that's now visible. Is that okay? So that
Yes,
should be nice.
that's good.
Should be nice and clear. So here we go. Computer who unlocked the universe. The talk has also been motivated by the International Astronomical Union, the IAU's strategic plan, and particularly the Global Outreach Project, which is Women and Girls in Astronomy. That was launched last February, and it's it seems right to celebrate that, particularly within this talk, where we celebrate women whose contributions are perhaps not perhaps so well known. I asked my astronomy GCSE classes, I've got 30 pupils, I've got 30 of them, in 2 minutes to come up with as many names of famous astronomers, dead or alive, and see what they come up with. And I could ask you guys, I suppose. It's nice to have a bit of interaction, but I'm not going to. It's not a very good format for doing that. But maybe just be thinking about, while I'm about to change slides, who would you name? 2 minutes, famous dead and alive astronomers. So we're going to think about women in astronomy, but here are the names that came up. So, who would you have gone for? What about Brian Cox? Okay, so in an age where fame is really measured by likes on social media, yep, you can say there's fame there. I'm not sure that Brian would classify himself as an astronomer. He's a physicist by training, but he's undoubtedly had an effect, the BC effect, on young astronomers and what he's been doing on the television. So there we go. That wasn't a surprising name to me. Stephen Hawking, I think in everyone's mind, must be an amazingly famous person, largely for the young, because he's been in films. Films carry a lot of weight these days. They don't read books. So if you're in a film, there is a chance that you actually know about these people. I think Stephen himself would have thought of himself more as a cosmologist, perhaps, than astronomer, and you may like to argue the difference between those two. But there we go. I think that he deserves to be there. Einstein always makes these kind of lists. He is the archetypal scientist. The media always like to refer to all scientists looking a bit like this. I was getting a bit like this in lockdown, I have to say, but luckily I had a haircut. But Einstein himself was, of course, really a physicist. He wasn't an astronomer and worked with astronomers, but of course he did an awful lot. He did an awful lot for astronomy. So 156 names were produced in 2 minutes by my 30 astronomers, not different names, I have to say, and 50% of those names were made up by just 4, perhaps the pillars of astronomy. So that was Copernicus, Tycho Brahe, who, of course, for many non-astronomers actually wouldn't be famous, but of course he really is a pillar of observational astronomy. Johannes Kepler, often called the father of astronomy, and Galileo. And that was their names. And we're all this is very Westernist, really. I mean, look at those people, and Northern Hemisphereists too. And of course, there are many Eastern and Arabic astronomers who contributed, but are not really known in our history books. We are very particular about who we write about. But please note, there are no women in there. In fact, of all those 150 names, there was one woman named, the title of my talk, the person in my talk, and that was by one of the girls in the set. So it was fairly telling to realize that we are pretty one-sided. There are no women actually in the GCSE specification, although in the supporting materials for it, there are 2. Both of them feature in my talk tonight. So could women not gain a name? Well, the answer is, apart from locally and at the time, the answer is pretty much no, and certainly not in the history books. So who knows of the contribution that Sophia Brahe made to Tycho's work? She actually did a lot of her own work at Uraniborg, but I very much doubt that anyone knows much about her. Caroline Herschel is, of course, much more famous. She won, she was the first woman to win a gold medal at the Royal Astronomical Society. She was the first honorary fellow, first woman honorary fellow of the Astronomical Society of London, which then became the RAS. But in her own right, is she as famous as William? No, of course she's not. And maybe that's right with the discovery of Uranus, as which has already been referred to. But nevertheless, they didn't really get a lot of fame. It was actually largely through husbands or family that people became famous for the women. And of course, the general medical advice was that nighttime work was not suitable for women, particularly in the late 18th century, because the fog, the cold and the damp was considered not for ladies, which actually probably explains why a very large number of women switched to solar astronomy. And that is a particular interest that happened. And one of these, of course, was Annie Maunder, who worked with her husband, Walter. Well, Walter Maunder is known for the Maunder minimum. Some people will know this solar activity minimum in the 1700s. And in fact, I was giving a lecture on solar magnetic variability, mid-Atlantic, as it happened. And Maunder's great-granddaughter, Annie Maunder's great-granddaughter, was at the lecture, so that was rather exciting for me. But again, not particularly well known. So what was needed in 1879 was a college, and this was founded, and this is Radcliffe College. It was needed to be somewhere where a parallel institute to the all-male Harvard College, which actually took almost 100 years to merge with it, where women could be educated, and they could then make a name for themselves. And the college was named after Anne Radcliffe. She was an English woman in the 16th century who actually married a Lord Mayor of London. And it's a nice connection for me because I'm a fellow at Green Templeton College, as mentioned, which is the Radcliffe Observatory on Woodstock Road in Oxford, if you know it. And it's also the place where the telescope that I run in the Marlborough Observatory came from. So Radcliffe is a nice connection with this, slightly obtuse connection. So the Harvard Observatory, which was then accessible for the Radcliffe College people, became a centre for the scientific-minded women. The women weren't actually allowed to use the telescopes, however. So at least that was a facility that drew the people in. And what then happened was that Edward Pickering, who, under his directorship from about 1877, he gathered a whole group of women as either computers, so mathematical women, or recorders, again, largely mathematical, but very, very precise. So women were either computers or recorders, and they were called the harem, Pickering's harem. They were seen to be ideal because they had meticulous cataloguing ability. They were paid 25 cents an hour. That's about £3 an hour today. They were directed by Williamina Fleming, who herself became a senior astronomer. And here you can see them working in not ideal sort of spacious conditions, but the idea of an open office was obviously still was relevant there. Williamina Fleming herself became a serious astronomer and is credited with the discovery of the Horsehead Nebula, that famous nebula, beautiful nebula in Orion. So Williamina Fleming was placed in charge of the Henry Draper catalogue. Some of you will know that, of stars, classifying thousands of stars by their spectra. It should be noted that actually the Henry Draper catalogue was financed by Mary Draper, his wife. So it really should be the Mary Draper catalogue. But there we go, it's the Henry Draper catalogue. And Williamina Fleming was cataloguing stars by the amount of hydrogen present in their spectra that they could see, and the Pickering-Fleming method was then named after them, and they classified the most abundant as A, and the next most abundant as B, and then C, and then so Another woman, Annie Cannon, joined the Radcliffe College in 1895. She became an assistant at the Harvard Observatory, so she actually was, I think, the first who was able to perhaps use the telescope in 1896, and she joined Pickering's Women. She classified over 300,000 stars by their temperature and their color. And this was very clever, and it revised Fleming's and Pickering's classification to form what we now know as the Harvard system. And that was Annie Cannon's system. It really should be called the Cannon system. And that is classifying stars from the hottest to the coolest, O, B, A, F, G, K, M. O, be a fine girl, kiss me is the mnemonic, or O, be a fine guy, kiss me, is the mnemonic that we still use in GCSE astronomy. And she classified these stars in their spectra from O to M, and indeed 0 to 9 as subclassifications. The Sun, as many of you will know, is being classed as G2, so a relatively cool star, somewhere sort of vaguely in the middle. She was actually, Annie Cannon was the first person to be awarded an honorary doctorate from Oxford University herself, so she was recognised at least. So let's get on to the main subject of my talk. You may have been thinking I was going a bit off at a tangent, but Henrietta Leavitt was born in 1868. She was born into a religious family. She entered Radcliffe College, taking an undergraduate degree, initially in Latin, Greek, sort of the classic studies. But in her 4th year, she did an astronomy course, gaining an A- apparently. She then joined the harem. She was assigned study of variable stars, stars that vary in brightness, in the small Magellanic Cloud. We've mentioned one of the irregular satellite sort of galaxies to the Milky Way. Well, the Magellanic Cloud, the small Magellanic Cloud, is one of those. As many of you will know, if you go to the southern hemisphere, the Magellanic Clouds sort of hang like clouds in the clear sky. They're amazing, beautiful objects. So back to Henrietta. She had a difficult life. She, at the age of 30, contracted an illness that made her go progressively deaf. She was a very, very hard worker. Apparently everyone liked her. She was quite quiet and unassuming, but worked exceedingly hard. And she was only 53 when she died of stomach cancer, and she never married. So in many ways, a life dedicated to and should be recognized for what she managed to do. So here's a nice picture of the small Magellanic Cloud, about 20,000 light years away. First seen by Magellan, the explorer, as he went down into the southern hemisphere. And it is, as I said, one of these satellite irregular galaxies to the Milky Way. It is actually quite close. It's only about 7 times the distance that the Sun is from the center of the galaxy. So if you look at the whole galaxy, the Sun, that distance, only about 7 times that. So it's a relatively close object in the sky. And originally, Henrietta found 16 stars that seemed to vary within the period of a few days. In the Magellanic Cloud, she increases to about 25, I think. And she found that they varied over periods of days, from about 1 day to about 127 days. And these are the ones that she studied. And luckily enough, it was then later discovered that the same type of variation was visible closer. And that's really, really important within the Milky Way. And so there was a way of seeing how far these stars were, and I'll talk about that. So this is the classic curve that she saw and was able to record of one of the stars. It wasn't actually this one. This is the first prototype star that was seen. I know your chairman was asking me how to pronounce these. Well, I think everyone does actually pronounce them in a different way, and perfectly okay. If you go online and you look at pronunciations, you get all sorts of different ones. I have to say that I call them Cepheid variables, and I call it delta Cephi. Whether that's entirely correct, but that's my pronunciation. Although I do say that the constellation, the place that delta Cephi is in, it's the 4th brightest in Cephus. So there we go. There are different ways of pronouncing these, but this Cepheid variable variation is absolutely classic, and it's really easy to find, because you have this quicker brightening and then a slower dimming. And this variability is not to do with the core of the star. These are huge stars, even up to 1,000 times bigger than the sun. They're yellow stars, so same type of spectral type. If you know about it, they are in the instability strip in the Hertzsprung-Russell diagram. So they're unstable stars, but the instability actually comes from their envelope, not the core. So it's all to do, we think, with the opacity of helium in their outer envelope. But what this does is it means that they grow and they shrink. And as the star surface area gets bigger, the star gets brighter, and it gets dimmer as it shrinks. And basically, the bigger the star, the longer it takes to do this. So the period of variation, here you can see one of period from maxima to maxima of 5.4 days. The period of the star varies with the brightness, and this is really, really important. I teach my pupils that it's a bit like deep breathing. So if you take huge breaths, it takes a long time, but the little Cepheids sort of, they pant, so they go in and out much quicker. Okay, so that's what she found. And here we are showing what they are. They are not variable because of anything outside happening. They are intrinsically variable. They vary because of instability within themselves. In about 1908, she found a linear relationship, and here's the plot of that relationship between the logarithm, so powers of 10, of the star's period and their magnitude and their brightness, so their apparent magnitude. And what you can see plotted here, I haven't included too many graphs in this, but you can see she plotted on the top the maximum brightness of a star, and on the bottom a minimum brightness of a star. So each vertical line is a star. So there is, each point you'll see has 2 points vertically, maximum brightness, minimum brightness, that's their variation. But what you can clearly see is that the period of the star is actually getting bigger with the brightness, and this is should be perhaps called Leavitt's law, but it's really often known as the period luminosity law. And this is important because when you see a star apparently bright in the sky, you don't know what its distance is, but the SMC, the small imaginary cloud, is basically, one can assume, the stars are roughly at the same distance. And therefore, this must actually have a relationship to their absolute magnitude. That means the actual brightness of the star. And so what she had effectively found was that the actual brightness of the star is related to the period. And that's incredibly important, because if you know basically how bright the star is, if it appears dimmer, that's purely due to the distance. And therefore what she'd done is she'd basically set up a distance scale, which is fundamentally important. Here is some variation pictures over a few days. This is a picture taken of Andromeda Galaxy, our nearest big galaxy to us. And there's a variable, a Cepheid variable, varying over 4 days. And it was the analysis of these stars actually in Andromeda by Edwin Hubble that really settled the argument. Howard Shapley as well had done this a little bit earlier, but it was this in M31, Andromeda Galaxy, that really settled the argument that these Cepheids were much, much dimmer than anything like in the SMC or nearby. And therefore that meant that the Andromeda Galaxy was that much further by orders of magnitude, and that these galaxies, which were fuzzy objects in space, these galaxies were nothing to do with the Milky Way. They were independent galaxies outside in the universe. So far greater distances. And this is Hubble's original plate, a picture of it taken from the Hooker 100-inch telescope in 1923. Hubble was looking for novae. These are stars that outburst and get suddenly bright over long periods of time. And it's a lovely thing to see an actual bit written. And he's written on the plate, actually he's crossed out N at the top, and he's written variable because he realized that he'd found a Cepheid variable. And there was this finding the Cepheid variable at vastly lower magnitude, so really much, much dimmer. that said how incredibly far Andromeda is away. So yeah, a scale of magnitude different. In terms of realizing this relationship between distance and brightness, you have to understand that brightness falls off with the square of distance. As you go twice as far away, it gets 4 times dimmer, 3 times further away, a 9th dimmer. It's all to do with the surface area of a sphere. I talk to my pupils about buttering toast, because if you put the toast further away and you spread the butter, you get 4 times less butter on it. But you can spread 4 bits of toast, and 3 times further away, 9 bits of toast, although you get a lot less butter. But there's the picture that sort of shows this, the intensity variation with distance squared. And this becomes what's known as a standard candle. Candles are basically the same brightness. So as you take a candle further away, the brightness gets less. It's a measure of distance. So all you have to do is know the brightness of the candle. And that is what Henrietta's work basically said. To a very simple observation, you find a variable star, you find that it's varying like a Cepheid. You then apply the law and find out how bright the Cepheid is due to its period of variation. Knowing how bright it is, you then observe it. How bright is it? Ooh, much, much dimmer. And that tells you the distance that this star is. And so really this is an incredible ability to use the Cepheids and find a standard candle to find a distance scale. This is what Hubble then used to measure the distance of galaxies, and particularly found that the redshift, the speed at which these galaxies were moving that he found from spectra, had a direct relationship with their distance. And this gives not only the Hubble law, which is the rate of the universe expanding. So he was able to see the universe expanding. It was good evidence for a condensed start. But this is all basically based on Henrietta's work. So Henrietta's work had not only opened up the scale of the universe, but it enabled us to understand how the universe is actually evolving. And therefore absolutely underpins our modern knowledge of astronomy and astrophysics. I should say that this is now being renamed the Hubble-Lemaitre law. Not a lot of people are using the Hubble-Lemaitre as the joint name, but it is officially now recognized that Lemaitre's work was fundamental also in establishing this law. I'm just going to have a little quick deviation because there's something called, which some of you will know, a trigonometrical method called parallax. And this was very important because it's a little bit tentative to say that the SMC, they were all at the same distance. We needed to find a Cepheid close enough to measure its distance with more accuracy. And the method to do this is called the method of annual parallax. And it's rather the same as putting a finger in front of your face. If you close one eye and then the other eye, your finger shifts. If you move your finger further away, it shifts less. So the shift from one eye to the other eye is a measure of the distance of your finger. And of course, we can do this by having the eyes being the Earth in June and the Earth in December. So across the base of that diagram, from half a year, 6 months apart, we can observe a star against the background and watch it shift. And so over a year, over 6 months, we can see it shift twice the angle on that triangle. There's a little bit of maths in there, but this is called the annual shift. And we've defined half this angle to be the parallax angle. And we define a new unit of measurement, therefore, called the parallax second, or parsec. And that means that if this shift is a tiny amount, although for astronomers it's quite a big amount, 1/3600th of a degree, that means the star is 1 parsec away. And 2 parsecs away, it'll be half that as the parallax angle. but it basically means that if you can measure very accurately a change in position of the star against the background. Now, only the closest stars can do this. You just can't do this for far away stars, but there are some close Cepheids that we can get a parallax measure, and nowadays much more accurately. But that means we can actually start to build the distance scale. We can actually understand how far away Cepheids are. Then we can use the law from Henrietta Leavitt to actually establish a distance scale. So just as a matter of interest, and I'm sure you do know this, but for the observers amongst you, we often go out to look at the saucepan. I don't like it being called the plough or the Big Dipper because I see a saucepan personally. But we look at the saucepan, and the right-hand edge of the saucepan points 5 times its separation, points up at Polaris, the North Star. Polaris is actually quite a complicated star. That's actually 3 stars, but the brightest part of Polaris is actually a Cepheid variable. So our friendly Polaris that we all know, only about 400 light years away, is actually a Cepheid variable. Not that one can see the variation by eye. I actually, someone's quoted this before, but it's interesting that Shakespeare in Julius Caesar writes, "I am constant as the northern star, of whose true fixed and resting quality there is no fellow in the firmament." So he wouldn't have known and wouldn't have been very happy that actually it was a variable star. But there we go. So we can now build a distance ladder into the universe and see how far away galaxies are. But this only works for relatively close because Cepheids themselves are not that bright. So what we need, Cepheid, the Polaris has a measurable parallax, but what we need is a better standard candle. And as I'm sure many of you know, what we have found is we found a type of supernova. So that is a huge star. Well, actually, these are a slightly different type of supernova, but there's basically an event which we pretty much know the brightness of, and they are much brighter, orders of magnitude brighter than Cepheids, and therefore by finding these, the same idea works. If it's very dim, it's because it's distant. And here's the only supernova type 1a that I have seen through my own telescope. Very sadly, on January the 22nd, I was at my observatory. Unfortunately, I was looking south. And had I been looking north, maybe, I've always sort of rather wanted to see a supernova, but there we go. Maybe I'd have seen this, but it was actually found by University College London. So students at the Mill Hill Observatory basically happened to be observing M32. This is a galaxy in Ursa Major. And they went away for some coffee, came back, and the galaxy looked different. It had this supernova in it. The next night, so within 24 hours, I turned my telescope to watch this, and actually had great fun. I'm sort of take things back to Galileo's day, really. I'm not an astrophotographer. I like getting the actual photons into my eye, and I like doing drawings. And so what I did for the next week or so, and we did have some clear nights, luckily, was I drew M82 and the supernova over a period of time. And actually from my drawings, I can chart the decaying light curve. The human eye, the ability to see and see different shades of darkness is actually very powerful. So sorry to all the astrophotographers out there, but I'm a very keen astro drawer. We now realize that the Hubble constant from these is not constant. We realize that the universe is not just expanding, but it's accelerating. That's certainly the evidence that we have at the moment, which is a bore because although we can think of it starting with a big bang, as so coined, it's hard to know why it should be getting faster. We can't find the energy or the forces needed to do that. And therefore we've called it, rather as a bit of a fob, we've called it dark energy. Can't see it, don't know what it is. But it's dark energy. But unfortunately, we now model that it consists, it actually makes up about 70% of the whole universe. So it's pretty important stuff. It's a bit of a bore that we don't know it, but it's very good for my pupils because they realize that it's all out there to discover. So all this started with Henrietta Leavitt. Henrietta Leavitt unlocked the distance scale beyond galaxies. And so great was the impact of her work, she was nominated for the Nobel Prize. But so little was she known that actually that was 4 years after her death. And you don't award a posthumous Nobel Prize. So very sadly, she is now recognized by a crater on the moon. She's recognized by an asteroid, and there's a telescope named after it, the McDonald Observatory. But she is not, I think, within that all-time fame. So I'm now going to move on from Henrietta to my second all-time great, a lady called Celia Payne. She added the name Gaposchkin on her marriage. She's English, and she studied at St. Paul's Girls' School in London. She was on a scholarship, not wealthy. She was brought up by her mother. At St. Paul's Girls' School, she was tutored by Gustav Holst, who persuaded her to go into music, which luckily for us in astronomy, she didn't. She then went on to Cambridge with a scholarship, where she was not awarded a degree. She was a woman, so she was not awarded a degree. But she was inspired by a lecture by Eddington, and Eddington gave a lecture on his Principe eclipse expedition, the expedition in 1919. So she was inspired to follow science. Originally, she was a Quaker, which actually was quite common within astronomers over the years. Famously, in her autobiography, she said that at school she conducted an experiment where she prayed for good results for 50% of her exams, and she didn't pray for the other 50%. Apparently, she did better in the ones she didn't pray for. So apparently, eventually, she became an agnostic, and I'm not sure whether that's at all completely apocryphal. Anyway, she moved to Harvard. She couldn't find any employment other than a teacher. And which is not a very enviable thing to be in the UK these days, given COVID restrictions, etc. But she joined Radcliffe College, and her inspiration had come from this Eddington lecture to study astronomy. And she was the first woman to be a professor at Harvard. So things had begun to move on, and she was actually able to work at the observatory. And in 1954, she discovered, discovered 1925, she discovered that the varying numbers of lines seen in the star spectrum related primarily to their temperature. And basically to how much the materials in the outer envelope of the star were ionized. And it allowed her to see that the abundance of hydrogen and helium were far greater than was thought at the time. The idea at the time was that the sun should have basically the same sort of chemical composition as the Earth in terms of proportions, and she basically disproved this. Henry Russell of the HR diagram fame actually persuaded her to not publish and to declare that her results were spurious, not entirely fair. He actually did later realize that she was correct. And in fact, in many journals, he is credited with the discovery of the lines and the hydrogen-helium abundance. So she had found a fundamental concept which went against perceived wisdom. It's attributed to her as another woman, but not perhaps in the history books. So she unearthed the very nature of stars themselves. So we have Henrietta Leavitt unearthing the distance scale, and Celia Payne really telling us about stars themselves. She's recognized by an asteroid, a volcano on Venus, and an IOP. I heard you talking about the IOP lectures, but an IOP prize was named after her in 2008, so a little bit of posthumous recognition. Okay, my third great is a lady called Vera Rubin. And Vera Rubin studied at Vassar College in New York. Then she went to Cornell. Unlike the two that I just said before, she actually did win numerous prizes in her lifetime. Her doctoral supervisor was George Gamow, who is credited with being a proponent for what is now known as the Big Bang theory. And in 1954, she discovered that galaxies cluster. So there is definite clustering going on with the galaxies. And this is really 2 decades ahead of the following research that went into galaxy clustering. So here's a lovely, much more modern image of clustering of galaxies, doing what she then became famous for. And here are the galaxies seen to be bending the light of galaxies far behind. So you see these extraordinary arcs of light which are being bent around this galactic cluster by something invisible that's unknown. It's called gravitational lensing, and this is her discovery, really. So she is best known, in fact, for her work on galactic rotation curves. So galaxies rotate around probably a big central black hole. And what you'd expect is the stars closest to the black hole would rotate fastest, and then it would get slower, 1 over r squared, probably slower as you go further and further out, 1 over r anyway, but it would certainly get slower. But this is not what we find. So we actually find that the stars further out in the galaxy are basically rotating at the same rate as those further in, not right at the center, but further in. And we call this the flat rotation curve. And here is an example of her work showing this very flat curve, not falling off in the way that you'd expect. And this is a problem for physics, because Newtonian physics would not agree with this. Classic Newtonian physics would not agree with this. And therefore, the only way to explain this is that there is embedded matter within and outside the galaxy. And this matter must be affecting the gravity and the way the stars go round. And so this missing matter was dubbed dark matter. It's another fob, really. So we didn't know what it is. It's now dubbed dark matter. And not only, therefore, do we have dark energy, which has been more modernly found, if you like, so we've known since the 50s that we had dark matter, but dark energy accounting for probably 70%, 70 to 75% of the universe, dark matter probably accounting for something like 20 to 25% of the universe, is pretty uncomfortable, really, because it means we know almost nothing about almost nothing. And that is not a great position to be in. But there we go, that was her work. It's interesting for some, perhaps, that actually this idea of dark matter is actually now being challenged for the flat rotation curve, has been for some time now, by something called modified Newtonian dynamics. It is possible to come up with maths where you alter the Newtonian dynamics of acceleration and you can obtain a flat rotation curve without dark matter. But it doesn't necessarily explain all the other things that dark matter can explain. But it might explain the flat rotation curve. So anyway, that's just a little extra bit. So dark matter is very elusive, and there is still basically no evidence of a particle or no candidates. Now, Vera did actually win the RAS gold medal. She was the second person to win the RAS gold medal after a gap of only 168 years after Caroline Herschel. So things don't move very fast. And that is the Newtonian expected curve. So very, very different. There is something definitely going wrong in the way that gravity is working. So there we go. We have an explanation from cosmologists of something called the cosmic web, and this idea that dark matter is modeled to make up a very large percentage of the observable universe. The largest dark matter detector that's trying is at Gran Sasso in Italy. And there was a potential discovery of something called an axion, but there's been nothing definite found. I have to say that I'm rather sad showing this picture because my outreach group at the Blackhead Observatory, the Friends of the Marlborough Telescope, we go overseas on international trips, and this was our international trip booked for March 2020. We managed to cancel it just a week before everything locked down, and we got our money back. But it was a sad thing not to go there, but possibly a sad thing for science, because in 2017, we went to Virgo near Pisa, the gravitational wave observatory, and very shortly after our visit, gravitational waves were detected at Virgo. And we also had been to CERN a few years before that, and down to the Large Hadron Collider. And it was very shortly after we'd been, the Higgs boson was discovered. So I have to say that I do hope we can get to Gran Sasso. 2022 is looking doubtful, 2023 possibly. So if we do, look out for the discovery of dark matter by 2025. So we can see if we can act our magic. Dark matter could be made up of small black holes. I think there are many different candidates, neutrinos, etc., might be possible. Indeed, last year, some researchers at Harvard actually suggested that small grapefruit-sized black holes might even be a Planet 9 candidate. And there's some discoveries actually very, very recently in the last week about black holes, and one of them has been mentioned. Basically, this whole search for clues towards dark matter will actually be led by the Legacy Survey of Space and Time, the LSST, as it was named when it was built, but the LSST has now been renamed the Vera Rubin Observatory in Chile. So she has had that recognition. Well, I don't think it is Planet 9, but we can talk about that. And here's my last. So I think one might expect people to have heard perhaps of Jocelyn. Obviously, unlike the others, she is still very much alive, thankfully still with us. I'm terribly lucky to share an office with her in Oxford, and I've known her for a really very long time. And I hope she wouldn't mind me including her in lectures as being an all-time great, knowing her very self-effacing nature and her incredible work that she's done in raising the profile of women in science. She has to be included in this talk. I hope her name is known. She is the only other person apart from Henrietta Leavitt to feature in the materials for the GCSE astronomy. And we're very honoured at Marlborough to have her as our president of our outreach group. So Jocelyn was working as a graduate at Cambridge under Anthony Hewish, and with her own hands helped to build a radio telescope, which actually is 120 miles of copper wire, so an amazing feat, which to study quasars, so very far distant active galaxies. But famously, at the end of 1967, she observed a repetitive signal, originally called LGM signal, for little green men. And it turned out to be the pulsing signals from a rotating star. This has been credited with as being one of the most significant discoveries of the 20th century. And of course, Hewish and Ryle, their supervisors, basically were nominated for a Nobel Prize and won the Nobel Prize in 1974. There are lots of people who refer to this as the Nobel Prize because Jocelyn didn't win it. But you might have seen that Hewish actually passed away a couple of months ago. So she didn't win the Nobel Prize. I think specifically she was a woman, was one, but also she was an undergraduate, which is probably the main excuse, because it was only the professors that tended to get the credit. So we now know the sources of these incredibly regular pulses. These are rotating neutron stars or pulsars. Unlike the Cephids, which rotate in days or vary in days, these vary in milliseconds. They're incredibly accurate. And they are very important. Just like the Cephids map out the distance scale going away from us radially, these map out the universe in a way around us, like lighthouses. They are very specific. Each one has its own pulse, just like a lighthouse. And therefore, in the same way, we can actually use them to map the universe and to triangulate positions. So I'm coming towards the end now, that when Pioneer 10 and 11 were launched, and indeed Voyager 1 and 2, they were launched with the classic gold discs on board. Generally, they were sent off eventually to head off out of the solar system. And famously, the location of the Earth is triangulated, that's the word, by 14 pulsars that Jocelyn discovered. So here's the Earth being marked by the position of 14 pulsars with known periods. So any alien finding the discs will know exactly where to come. This is where we are, and we'll have no problems. We'll have no problems finding us. So Jocelyn did not win the Nobel Prize, but she has, for her 1967 discovery, she's won many awards. She has become this year the fifth woman to win the RAS gold medal. And most notably, she won the 2018 Special Breakthrough Prize in Fundamental Physics, which is actually worth $3 million. So 3 times the Nobel Prize. And as a reflection of her dedication and generosity, she donated the prize entirely to be used to further the careers and support young women researchers from underrepresented backgrounds, also including refugees. And the Institute of Physics funds these graduates in the UK with a scholarship fund. So I'm going to end with just a summary of some of their recognition, which I've already mentioned for Henrietta Leavitt and Cecilia Payne and Vera Rubin, and then Jocelyn Bell. Many prizes, too many to mention, really. But I think it's a clear message that, if we go back to that first question, how many of these could you have named? Well, I think many who study astronomy will have come across the names. But for the general person who is undoubtedly interested in astronomy, there's a huge rise in interest in astronomy. These incredibly important women who've really determined a lot of our astronomy and cosmology have largely been written out. So I hope that's been of interest, and thank you very much for listening, and we'll try and organise some question answering if I can. Thank you.
Charlie, thank you very much indeed. It's been quite a fascinating presentation, and I've really enjoyed it. I'm sure others have too. So as we get on to questions then, I actually have posted some. You probably haven't looked at the chat, but the first that I immediately had to ask, which was when you mentioned the IAU strategy for 2020 to 2030, my immediate question was, do they have any strategy to revise their definition of a planet? I won't ask you to actually answer that, but it's just something.
I'll answer it in parts. I was peripheral to the discussions in 2005, but wasn't yet a member of the IAU, which I am now. Of course, Jocelyn actually chaired the discussion and the argument. I am going to say that rather excitedly, in September 2005, I actually saw Pluto through the telescope, absolutely at the limit of my telescope's magnitude. So it was at magnitude 13.9, and the telescope can go up to 14 theoretically. And myself and a group of 12 people actually saw it. And very few of my colleagues have actually seen Pluto. I saw it on the Monday, I saw it on the Friday, and it had moved just the right amount. And then Pluto was deplanetized, and I claim that I'm probably one of the last person to see the planet Pluto. So anyway, there we go. Obviously, it was a huge argument. I went out to Flagstaff in 2017, and I love the observatory there, which has in the visitors center 3 boxes when you leave. If you think Pluto should be a planet, put your money in here. If you think it shouldn't be a planet, put your money in here. And if you don't care, put your money in here, which seemed a really good way of doing it. I think that the definition was done. And at the time, a lot of it depended on various things. There wasn't the discovery of Pluto's other moons. There wasn't the discovery of the incredible variability on Pluto's surface. There had been the discovery of Eris, and of course Eris was thought to be bigger. Now actually it's revised to be probably about the same size. So yeah, should we revisit it, or should Pluto really be? I think the cleared orbit and not other, we're going to find other objects like Eris, Haumea, Marke, etc. So we're going to find other objects, and do they get to be planetary status? I mean, should Eris be a planet? I think there are many reasons. I have to say, no, I won't. But perhaps I better not declare, because that I might get vitriolic emails. But there we go. I think that's where it is. Will it be revisited? I'm sure there are discussions about the definitions, especially with all the discoveries of the exoplanets, because we now are absolutely sure that we really hadn't much of a clue about planetary formation, and that our solar system is not at all how they are definitely going to be. It's not at all special. You see planets in all shapes and sizes, and therefore I suspect there'll be more discussion of what planets really are, but I don't know. I'm not part of the inner planetary discussion sanctum.
Well, I actually have a presentation called "Is Pluto a Planet?" in which I demonstrate that according to that definition, Jupiter is not a planet. It fails all 3 criteria.
My pupils are always quite interested in defining the moon in various ways too, and How does that sort of sit in things? And you might say, well, okay, it doesn't go around the sun, but anyway, we won't get into more stuff.
Let's leave that.
Anyway, good question. Dear old Pluto.
If you do have any other questions to put to Johnny, can you please put them in the chat, even if you have already done so? The reason being that 10 minutes ago, I had to reboot my connection. And so the things that were...
I can see the chat now. And what about star grades, WRNS? Well, yes. Certainly, one even tends to teach about oh, be a fine girl or guy, kiss me right now, smack, RNS. I don't know that the W is often included, but over time these things change. What I was taught at university in the early 1980s bears very little resemblance to what I teach now in astronomy. I mean, so many things. Astronomers are theories. The facts are pretty hard to guess in astronomy, and these theories change. And as I said, I think I was aware of dark matter at university. I wasn't aware of dark energy, obviously, but we now do live in an environment where we could be very wrong about things. And I think we have to be very open-minded. For an observation astronomer, which I suppose I really classify myself as a director of an observatory, I am observational. I used to study more the theory of stellar evolution, but now I'm an observation astronomer, and I know what I see. Well, I suppose I know what I see in my own interpretation. I'm not entirely sure what it might be, but there's obviously very little that we necessarily know for fact.
Well, and as you say, your teaching has changed, but then our complete understanding of astronomy keeps changing. I mean, it was only a couple of 100 years ago that, as I said, we doubled the size of the solar system. We started to find other planets that we had no idea about before. And then just 100 years ago, we discovered really that other faint fuzzy blobs in the sky are entire galaxies. And now we know from the Hubble ultra deep field picture that there are galaxies absolutely everywhere, but most of them are just too faint for us to see generally. But astronomy keeps changing, and now
I mean, it makes it exciting. It does make it exciting. It means that we have to keep on rewriting the GCSE syllabus. At the moment, we're on a 2017 rewrite, but I suspect within a couple of years we're going to have to rewrite something. But it does make it exciting, and it makes it exciting for the pupils particularly. And at the top level, it's a very you get a very driven pupil. I mean, yes, it becomes very mathematical, whereas astronomy per se, observation astronomy, doesn't have to be. But astrophysics, and when I get involved in the Olympiad, which I do, we come across pupils who are really extraordinarily driven and clever. But astronomy enthuses them. So yes, they may be very good mathematicians and very good physicists, but they have this drive of enthusiasm that comes with all these undiscoverable ideas and very complicated ideas in astronomy. It is, I say to all my pupils, what my professor told me at university at the beginning of my degree. He said, you're absolutely going to love this subject. And I did. I used to go to every single lecture. I used to get up early. They were always early lectures. Unless you'd been observing all the night before, you were let off lecture one. But he said, you're going to absolutely love this course, but don't think about it. And it is true. You accept what people say about astronomy, and you then can move forward. Because if I say that that's a light year, the distance that light travels in a year, well, don't think about it. But if I say that that is 2 light years, you just double it. But if I say that's 1 million light years, then that's 2 million light years. Then it's just you just sort of accept it. You alter your scale of thinking. But it is, well, as you wouldn't be a member of this astronomy group if you weren't excited by astronomy.
Well, that's it. That what we say to people, especially ones who say, "Oh, I don't have a telescope," and I say, that's not a requirement.
It's my first bit of advice in astronomy. I have 3. I'm going to just voice it again here. I have 3 bits of advice in astronomy. One is don't get a telescope, because they're incredibly difficult to use. And in my knowledge, all you measure with telescopes is how quickly they go back in their box and up in the attic. They're really disappointing, and people don't understand how to use them. So that's my first bit of advice. My second bit of advice is don't go out at night. because if you go out at night and it's really full of stars, I mean, you're lucky to get a clear night, but you can't find your way around. There are too many stars. Go out at sunset. As the sun sets, the stars come out in order of brightness, and that's how you learn them. My third bit of advice is don't learn constellations, because constellations, dogs, bears, dolphins, well, you're pretty lucky if you see any of them. And it's much better to learn asterisms, which shapes that you understand, and you can make your own shapes. So those are my three do's for astronomy. But you're absolutely right. It's people can get very enthused, and we have very, very young, extraordinarily bright young children. My youngest is actually 3 that's been. I didn't get a lot out of them, but we had a 5-year-old who actually could name probably a dozen asteroids within the asteroid belt. And the children are sponges of information and get very excited about individual things. And sadly, we somehow don't tap into that enough. We get them, if you can get them interested in sort of 10, 11, then you can. But sadly, this interest sort of wanes and everyone starts being too busy and doing other things.
Yes, I know when I was about 10, I could name about 100 features on the moon. I don't think I can do that now. That's it. Anyway,
so what percentage of women are at your lectures? Well, if it depends who I'm lecturing to. So I mean, I try and lecture to as mixed variety of people as possible. What is interesting, as I mentioned at the beginning, is that in my experience, the number of girls and boys is always nearly very equal. When you have an astronomy course, you have a physics course, totally different, but an astronomy course at either primary, secondary or tertiary level, then they're nearly always pretty balanced. But there are many problems for women in astronomy, as there are in science, for progression and pay and treatment. But it is interesting to look back and actually look at how history hasn't really focused on some of the main discoveries and the main proponents.
Mm. Well, as regards women at Hag, Alan, in fact, Anne is there tonight. Anne, weren't you a member of the original evening class? Alan is nodding.
Can you hear me?
Yes.
Yeah.
Yeah, I was, yes, back in 2003, 2004, January 2004 it was, wasn't it, Alan?
Yeah.
Yeah, and I think we started this group, after 1.5 years of different lectures that we had. So we started it in 2005, September 2005. I think there are 3 or 4 of us, because Frank's on tonight from the Cotswolds. So Frank's on tonight. There's 4 of us that are still here 18 years later. And I know that because my daughter had just been born, and I was going out of my mind with boredom and wanted to use my mind again. And that's when I joined the lectures that we had through the WEA. And our first president was actually a woman, Marion.
Chairman,
Sorry, yes, president. Yes, of course. Yeah, but I found your talk absolutely fascinating. I really enjoyed it. And of course, there's always been women that are very interested in pursuing scientific discovery, and it's just they're not very well known because that was the convention today, wasn't it?
But there was every obstacle put in their way. I mean, for women not to be able to actually use the telescopes.
Yeah.
It's not entirely fair, but credit should be given for the same amount of work. And there are a lot of things still to solve. But I have to say, I mean, Jocelyn is someone who has really dedicated her life to raising the profile, and one would hope that people do know about her. I mean, outside that world, and she has been rewarded for it, but quite rightly so.
Right. Any other questions from anyone? While we might be waiting for more to come in, can I just say that I'm also the meetings organizer for the Federation of Astronomical Societies, and our next in-person convention which I have to say may be delayed because it was going to take place in March next year. We might have to postpone it a bit, but it is going to be on the subject of women in astronomy. And I am delighted that our keynote speaker will be Jocelyn Bell Burnell. And because she's based in Oxford, that's where it's going to take place. And I'm setting up other female astronomy speakers. So you'll see news about that in due course. So, so Jeff has said, talk was so good. I can't think of a question, which is very unusual for me. And Stephen,
well, that's probably lucky for me. I try my best with these questions.
That's okay. Stephen and others have said how much they really appreciated your talk. Thank you very much indeed.
Okay.
So with that, I think I will say thank you on behalf of the Society.
It's always hard to on Zoom to know how one's reacting, and I can usually, at a lecture you can pretty much judge. One hopes people don't walk out or fall asleep, but on Zoom it's not quite so easy. Anyway,
your talk.
Anyway, it's been a pleasure to come and chat, and I hesitate to say, but if anyone is down in the Marlborough area, then do look me up. We don't have a lot of slots at the observatory for astronomical societies. We prioritise schools and teachers and other groups, homeschooled and people that don't get access to observatories more often than not. But nevertheless, you'd all be welcome. And if anyone's got any other questions or anything they want, then I know that your chairman's got my email. I'll be very, very happy. So I'm going to head off and leave you. But good luck with everything, and let's hope we eventually return to some kind of normality.
Thank you again very much, Charles.
Clear skies. That's what we want.
Okay, thank you very much indeed.
Okay.
That was a fascinating talk, and thank you very much for coming along, giving your time. It's most appreciated.
Okay, thanks, Alan, very much. Okay.
Thank you to Jerry as well for organising another wonderful talk for our group, which is brilliant. Our next meeting, a little bit of a change to the programme, January the 12th. Our next talk is missions to near-Earth asteroids. I mentioned that at the beginning, that there's a mission already on the way. So I'm sure that's going to get a mention in that talk. John Davis, January the 12th. And I think that just about wraps up tonight. So thank you from all of the committee of Hertford Astronomy Group. We wish you all a Merry Christmas and a Happy New Year to all of you.